Hi. Before starting this video, so how this video is going to be helpful for you. So I have added Q&A session of this summer that has been answered by Amazon experts, ML experts, and the scientists. So the questions and answers are really insightful and really helpful. Go through them; you will really enjoy it. Thank you. Hi, hello, good morning, everyone. Today is day 2 of Summer School 23, and today they are going to teach us deep neural networks. So they have sent us the link. To join the webinar. Today it is from 9 a.m. to 12 p.m. Indian Standard. Let's join the webinar. And today's topic is deep neural networks. More 5 minutes to go.
In this session, we are going to learn about deep neural networks and why they're used and how they're used. And we will cover three main parts of deep neural networks: MLP, or the multi-layer perceptron, convolutional neural networks, and finally, recurrent neural networks. So first, in this first part, we will discuss about deep neural networks and the multi-layer perceptron concept and what it is and how it is used. And in the next two sessions, we will go over with CNN and RNN data sets. And
okay, this is pre-recorded.
Already built a linear model
increase the
these
speed.
details, right? So next, in this session, we will cover some historical context about why is deep learning being used and what WQ.
Okay,
and
today they are
we
showing some
call this
program
backward method on
examples.
this output, and then we can look at the gradients of the individual.
So first session,
These are a few key
second
takeaways
one
from
is
the session.
about
We will begin by looking at a few applications of CNNs.
CNN.
Where are CNNs used? And then we will move on to why we need CNNs.
Let's continue
So
the
we
course.
already learned about MLP. So why can't we just use MLP? So there's a need for a special.
Okay, we got break. I'm skipping this break. I'm using this extension, video speed controller. This is helping me to speed up the video. This is pre-recorded video. And this time they are showing us code examples and in the notebooks. So this time it is good.
Hi, welcome to part 3 of deep neural networks. This is the second session of Machine Learning Summer School by Amazon India. I am Faizan, your tutor in this session, and I'll be walking you through what are recurrent neural networks and why we use them. So in this session, we will cover all the details about recurrent neural networks, like what is a vanilla RNN recurrent neural network, what is its structure, and how is it trained. We'll also see some of the challenges facing these type of networks and how are such challenges alleviated from these networks using something called as LSTM and something called as transformers. Finally, at the end of this session, we will go through a exercise video, which will be a small lab, and we'll see some code examples in that. In the first session on multi-layer perceptrons, we actually talked about something called priors or inductive biases. So in here, what I mean by inductive biases is that what kind of structure is our model
Let's
encoding
continue the
in the
course.
network.
Done with last session. Now at 4 Q&A session will be there. That will be live. That won't be recorded or something. So yeah. Today it was basically on neural networks and CNN, RNN, and more variations. Like there is BART in the Google. They spoke about.
Yeah, so momentum helps in faster conversion. So if you have, say, 3 samples which have gradients in the same direction, then if you have momentum, you can converge more learnable parameters and then also add more epochs accordingly. And that helps you in converging faster. And at the same time, it can have a kind of stabilizing effect where if you have some samples in your data which is actually going against the trend, where say if you have 10 samples which are telling your network to go in a particular direction and one which is telling your network to go in the other direction, it might be the case that the one which is telling you to go in the other direction is actually wrong and the other 10 are correct samples. So in this scenario, by using momentum, you are actually not letting that one sample add a noise to your training, and it actually adds a stabilizing effect. So that can help in both speeding up accuracy as well as improving generalization, and also because it kind of increases the learning rate, it can help you in escaping local minimas and getting better generalization.
Is there any difference between regularization and generalization? Yes.
Yeah, so generalization is something which we want. So generalization is tells you that your model can handle a wide variety of samples correctly, and it is not overfit. So if your model is overfit, then it is not generalized. Regularization is techniques to make your model generalized. So generalization is the goal. Regularization is the technique you use to make sure that your model does not fit and it generalizes. So regularization and techniques, generalization is kind of what you want to do.
How to know we have to choose a DNN or normal ML model? So we can basically choose on the basis of the problem, right? So for example, if you have a problem like image classification, then DNN makes much better sense compared to a normal ML model, right? On the other hand, if you have a simpler tabular data problem, right, then you might want to choose something like a tree-based method like XGBoost or LightGBM, right? Similarly, if let's say you want explainability in your models, like you are making a model for banking domain, right? There you might choose decision tree because you want your model to be explainable to stakeholders as well. So depending on your domain and the relevant literature, you will choose DNN versus normal models. Yeah. How to calculate weights for the hidden layers before convolution, either in RNN or CNN? Yes.
Yeah. So you usually don't use hidden layers before convolution. Usually whenever you are using convolution, you start with convolutions. You can do multiple convolutions, or you can do one convolution and then you can do pooling. And then after a few layers of convolution and pooling, you can use hidden layers. Similarly for RNN as well, it's more common to have recurrent layers before and then the hidden layers. So you will usually see the hidden layers just before the output layer and after the recurrence or the convolution layers. In terms of how do you calculate weights, you usually initialize the weights as something, and then you use the standard backpropagation algorithm to find the weights, the correct weights for your model. But to initialize the weights itself, there are some standard methods like Xavier initialization, etc., which can tell you what are good values to start your training with, and then you will use backpropagation to get the ideal weights.
Can you explain the concept of transfer learning in deep learning? Yes.
Yeah. So if you have a problem and you start with a randomly initialized weights and you train the model completely using backpropagation, then you are training the model from the scratch. But usually training the model from the scratch is not the best idea, because you would have similar you would have a lot of models which all solve similar problems but not your exact problem. And in this case, what you can do is, instead of training the model from the scratch, you can take a look at models which solve a similar problem and they do it very well, and then you can use that as a starting point and then update your weights on those initial weights. So for example, in an image kind of a scenario, you might want to solve a problem for the medical domain, but the amount of data that you have for the medical domain is very small. And if you train it using that, you might not get the desired result. So what you can do instead is you can look at big standard problems like image classification, which use the image data set, which has a lot of data. You can use models pre-trained on that problem, and then you can use that as a starting point and then try to train your model with the data that you have. And you will see that your model learns things faster, because a lot of the things that a model has to do is common across a lot of models. So for example, for images, the basic textures, patterns, and shapes that a lot of objects have is similar across a lot of domains. Similarly, for text, you might want to do text for medical domain for, say, doctors or whatever. But at the same time, you can just use BERT or Llama or whatever large language models which are trained on generic text and start off on top of that instead of starting from the scratch. And this is transfer learning, where you transfer knowledge which was acquired for a different task, for a new task for which you do not have enough data.
Can you please give a brief on the below topics? Neural machine translation, meaning of attention and self-attention. So neural machine translation is nothing but the domain of translating from one language to another. So usually you will have a input in one language like English, and you want to translate it to Hindi, let's say, right? So for these you have models which have a encoder and a decoder part. the encoder is meant to basically encode the incoming sentence in the source language into a representation, which again the decoder uses to decode into the target language. There are various models for this, including previously RNN models, and now there are also transformer models which also do this, right? So depending on your use case, you would want to pick a model of appropriate size and accuracy and then go for with that. Attention and self-attention, we do have a session that comes up later and covers these in much more detail. So we would not dive into those right now. There is a session which has more details. In the session, we were told that Amazon uses DL to classify images that we see on product pages. Can you please brief on the architecture or model that is being used there? So we cannot give you specific details, but maybe Yash can tell you a little bit about the kind of models that he has seen and used. Yes.
Yeah, so the kind of models that you would typically see in computer vision problems would be the ones which I've already mentioned. Like you will, a few years back, the default choice was using ResNet or some variant of ResNet for a particular problem. So you will typically start with a pre-trained model and then fine-tune it or do transfer learning for a specific domain. Now, instead of ResNet, you can use a vision transformer, which is the more recent update which we have, and kind of like a default, which is very common now. So again, you can take a pre-trained vision transformer, which is trained on the ImageNet data set, and then fine-tune it for your particular needs. In a lot of scenario, you might not even have enough fine-tuning examples, and you might want to do something without a lot of guidance. In that case, there is another popular model called Clip, where you can which does both image as well as text encoding, and it embeds them into the same space. So you can compare text with an image using the Clip model. So Clip is another popular choice which is there for a lot of problems. So usually you will start off with one of these models and then fine-tune them according to your need.
Yeah. How can we handle variable length sequences when working with RNNs? So essentially the idea to handle variable length sequences is to do padding. So let's say in a single batch you have a sequence of length 8 and a sequence of length 12, right? So you will pad the sequence which has length 8 with 4 more pad tokens to make it length 12, and then you can feed it into the RNN, since the both sequences are now of the same size, right? So you would use some kind of padding. In case of RNNs, depending on your problem, you might either do left padding or right padding. Most classification problems, you might do padding on left or right. It would not matter. You would just have to train the pad token. So that's mostly how you can do it.
Models like arc phase and which are very accurate, and usually the way these models are trained are you take a convolutional neural network, you have a large data set of faces and you have identities. So you might have say 10,000 identities or 20,000 identities or different identities, and you will have a lot of faces for each one of them, and then you train it as a standard classification problem. But instead of when you're actually using it, instead of using the prediction for which class it belongs to or which identity it belongs to, you instead look at the embeddings and you compare the embeddings to see if two faces are matching each other or not. So that way you get a generic model which can compare faces instead of just a model which can predict if this face is of this person or not. So that's usually the way these models are trained. And you can look at arc face, which is a popular choice, but for a lot of scenarios, getting a good face recognition model is tricky because most of the data has some issues with respect to licensing and ethical concerns. So you might want to check into them.
Next question. Check. So how can a sequence-to-sequence model transformer architecture be used in text summarization? What are the main advantages in using it? If you want to take it.
Yeah, so you can use an encoder-decoder style way of doing it. So this is just one possible way where you look at a sequence of inputs and you use an encoder, which can be an RNN, an LSTM, a transformer, and with that you generate one output embedding, which summarizes the particular thing for you. this summarization can be used for various different tasks, right? Like it can be used for question answering, it can be used for translation, it can be used for summarization as well. So in summarization, you will take this output embedding, and then it would be the input to a decoder which starts generating text, and it will generate a text ideally which is of this which summarizes what you had already filled as input.
How can we determine the correct learning rate? So the correct learning rate will depend on your particular batch size and your problem. So essentially, you will start with a standard learning rate that would be known for your particular domain by doing some literature search and survey, and then you tune it to your own use case. So for example, in fine tuning, you start with learning rates like 10 per minus 4 or 10 per minus 5. While for pre-training or for training from scratch, you can start with something like 10 per minus 3, right? So you start with a particular learning rate, and then based on whether your problem is converging fast enough, you would either increase the learning rate, or if you are facing exploding gradients and your loss is suddenly increasing, then you would want to decrease the learning rate. So depending on how your training loss behaves, you would try to change the learning rate. Apart from that, obviously using learning rate schedulers and warm up would help. Learning rate warm up would help in making sure that the network stays stable even at a higher learning rate. Right. Yeah. I want to make a chatbot which gives answers on the questions asked. I want to train it on a dataset of question and answers and get results as much dynamic as possible in genetic answers. What should I do? I don't want to use GPT calls or fine tuning. So if you don't want to use GPT or fine tuning, then what you can do is you can take a pre-trained model that is already available open source, and using that model, you can basically you can use a retrieval augmented generation paradigm. So in retrieval augmented generation, you will search your document store for similar documents as per the question, feed it to the model, and then the model will answer on the basis of those documents. So in your case, you can actually use something like a sentence transformer and encode your questions and answers, and then do it through retrieval without training also. So in simple sense, retrieval augmented generation and a pre-trained model could help. How has Amazon leveraged transfer learning techniques to enhance its various services and operations? So essentially, a lot of models that we train, we don't train them from scratch, right? If we have a data that is for, let's say, natural language processing domain, then we might take a pre-trained model and then we will fine-tune on top of that instead of training from scratch, right? So it's similar for image domain and for speech domain also. So we tend to use these pre-trained models and then fine-tune them on our own data to make them specific to our problem. Any tips and tricks for practicing deep learning? Yash, one figure.
Yeah, so there are various ways where you can practice deep learning. You can try to solve challenges on Kaggle. You can try to implement recent papers which are there, and try to write about them, blog about them, maybe create GitHub repositories which you contribute to. You can find other GitHub, like not just yours, but you can find other GitHub repositories which you might want, which are looking for collaborators. You can find professors in universities who are working on research problems and looking for people they can work with. So there are various, like these are some of the ways that you can practice deep learning and and get better at it.
How can we combine global and local attention models? I'm working image captioning project where I use local for the text and global for the image processes. Yes, you can take that.
So I'm not sure what you mean by combine, but like as you mentioned, right, you can use local attention or you can use cross attention. So local attention is usually for text where you are using it within the same sequence, and you can use cross attention where you are actually getting it from a different part. So I'm not sure what you mean by combining them here. You use both, and both of them would have parameters which should get updated and be used.
Given a data set on which we want to train a CNN, how do we actually arrive at a good architecture for the model? So my suggestion would be to go with what the literature in your particular domain is doing. For example, if you have a lot of data, then you might be able to train something like a ResNet 101 or a vision transformer also. But if you have less data, then it might be better to train a ResNet 18 or ResNet 34 model, right? So you should go with how much data you have, and also with the particular architectures that are better for your particular domain that has been in your domain. And then based on that, you can choose what architecture to pick up.
Sorry, which question was this one?
This is by Samiksha. Certain deep learning models require annotated data for training, but some do not. Does accuracy of detection depend on this?
Yeah, so usually when you have a deep learning model which does not require annotated data, what it is trying to do is it's trying to learn something from the pattern itself. So for example, in a large language model, it would be some just input text and solving problems. So the way you train it is by creating a different prediction, right? Like you can have a fill in the blanks kind of a situation, or predicts the next token kind of a situation. Similarly, in images also, you can do something similar where you can have an empty patch and you can try to predict that empty patch, or you can use autoencoders where you have an image, you compress it into an embedding, and then you try to generate the output again from that embedding itself. So usually there are both supervised and unsupervised models, and in general, it is likely that the supervised models are going to perform better. And the reason for that is if there is an unsupervised way where you can solve the problem better, then you would use the unsupervised way first, get a base model, and then use your supervised data to improve the model further. So usually when you do have annotated data, it is likely to improve the results that you have. Prevent overfitting as a first resort, L1 norm, L2 norm, or dropout. I think you can start with L1 and L2 now and then go to dropout. But again, I think there's no reason why you have to restrict yourself to it. You can try both. So there's no. If you have limited experiments, maybe you can start with norm and then go to dropout.
How can we reach global minimum when there are several local minimums in 3D? So the current opinion about global minima and local minima is that when you have a over-parameterized model, right? So an over-parameterized model actually does not get stuck very easily in bad local minimas. It's quite easy to reach a minima which is good enough. So we are not guaranteed to reach a perfect global minima every time, but we will reach a minima that is good enough for our particular problem. So as a result, it's not a lot of concern whether you reach global or local minima, because at max you can visualize it in 3D, but when your model has like 1 million parameters, you can't even visualize or confirm whether you're in the local minima or not. So as a result, it's not really very important to worry whether we reach there or not, but rather choosing an over-parameterized model helps us to make sure that we reach a good enough minimum. Can you share some resources to learn more about LLMs and also get hands-on experience on using Hugging Face? So Hugging Face Transformer Library itself has a very good documentation and multiple examples. So I would definitely suggest to browse their own documentation as well as their model and dataset hubs to get an idea of what kind of models they have, and from there you can get started. Through EEGs and using them to control a wheelchair, how do I take care of the variability of data which I will receive, as everyone have different EEG signals? This is a very interesting question. So deep learning in medical domain is pretty hard thing. So, and EEG machines are really noisy as far as I know. As a result, you would want to gather as much data as you can, And apart from that, I would say that if you can work or collaborate with someone from medical domain, that would be much more helpful to you, since doctors and medical domain people regularly interpret EEGs, right? So interacting with a domain expert will tell you how to use EEG signals more efficiently. Just putting a model in front of the EEG signal would not give you the intended result, given that usually EEG signals are very noisy. Yes, you want to take any question that you find interesting and all, you can take that. We're almost out of time, so.
Yeah, I was just going through them. I'll just take whatever I was looking at currently. So there's one, I tried experimenting with vision transformers with 2-class image classification, but the GPU RAM was entirely exhausted entirely after 5 to 6 epochs. How do we optimize and tune the model? So in this case, I would say there might be some memory leak or some kind of a variable which you are storing, which is increasing the GPU RAM, because usually you do not see the GPU RAM usage change much across epochs. So in this case, there might be some variable which you are storing which is still in the GPU. So maybe if you are storing some results and you're not converting it back to CPU, or there's some variable which is constantly getting added to and not being deleted. That is a possible reason, because otherwise, usually if a model runs for one epoch, it should be able to run for as many epochs, and that doesn't, like, there's no increase. There should be no increase in GPU RAM across epochs.
Sure. Does cosine similarity comes under RNN? If not, can you brief? So cosine similarity is more of a metric for calculating similarity between vectors coming from different representations. It's not coming under RNN, but rather it's more of a metric that you compute, like L1 distance or L2 distance, while RNN is more of a modeling technique or a model that we are trying to use for a particular problem. I'm doing a project on threat detection, action detection using computer vision. Can you give me any suggestions in selecting the model? I'm planning to embed Raspberry Pi and CCTV camera, and the faces will be in smaller in size. So I would definitely suggest action recognition as a domain that you should look into. There are various models and approaches in action recognition which try to train models for recognizing action patterns, right? Instead of trying from scratch a CNN model, you should look into action recognition models and how they do it, and then go from there.
So one good resource for checking out models. So I see another question which is about how do we choose a CNN model. So one good resource for checking out the different models and choosing between them is Papers with Code. So you can go to Papers with Code, and in Papers with Code, they usually have a table with the different models and how they score on a particular benchmark. So you can check out the page for a particular benchmark on Papers with Code, and you can see what are the results there. It can also help you in ideating what kind of models you can use. So action recognition was one idea, but when you are going through Papers with Code, the website, you will see what are the other kind of standard problems in that particular domain, and you can see what are the standard data sets and which type of model would be a good fit, and then within that data set, what is the state of the art which would work best for your particular problem. So that's a good resource to check out different benchmarks, data sets, and models.
How can I detect houses in satellite images using YOLO? Kaggle does have data sets and competitions regarding satellite imagery, so I would ask you to first take a look at that, and that would give you a good idea on how to get started with using satellite images. Kaggle has a lot of competitions on satellite imagery, so start there. My personal question: what does Monte Carlo tree search do? So Monte Carlo tree search is more of a tree-based algorithm which is used for detecting what path to follow in a reinforcement learning kind of scenario or in a agent-based scenario, right? It's we do have a session in RL, I think. So in the RL session, you would know more about these kind of things about how agents work and decide on the course of action. MCTS is one such algorithm, that is used in how do agents try to figure out what to do as a next step by searching through the environment in a tree fashion. Okay, one last question I'm taking, I guess. Can you tell the basic difference between PyTorch and TensorFlow? So this is a question which is more of a preference rather than a strong difference, which is that most of the research currently has been gravitating towards PyTorch uses, and knowing PyTorch definitely helps you to read more papers and read their code as well. So definitely get to know PyTorch. If your use case specifically requires you to use TensorFlow, there are certain places where TensorFlow is good, like TF-Lite is very good for running on the edge. So in those cases, you might want to know TensorFlow as well. These are both good libraries, and PyTorch is more in the research domain currently. Any question you want to take, Yash, or I don't have anything else that I can take.
Yeah, I think we are already, we can close.
Sure. Okay, thanks everyone for joining the ML Summer School 3rd edition DNN, CNN, RNN session. It was great to be answering your questions. There's a lot of good questions here, and some we were able to get to, some not due to the restriction of time. But I hope we were able to help you. Thank you so much, guys. Thanks, Yash, for helping out as well.
Thank you, everyone. Bye.
Thank you. Bye-bye.